Greetings. My name is John Gabriel, and this is the New Calculus channel. Today, I'm going to talk about an article that appeared in the BBC Online News. It's an article about measurement, and it has a lot of interesting things to say. And I've no doubt that both the author and those who are mentioned have actually been reading about my ideas, but somehow they still don't get it, which is rather unfortunate. But let's see why they don't get it, and let's discuss the facts about measurement. Let's begin. So, I'll get back to this article in a moment, but let's go to the BBC article. It says, the measures that don't need maths. Now, for those of you who are not as well traveled, in the UK, they don't call maths math, but they add an S at the end. It still means the same as math here in the US. Okay. So, the author is Adrian Bernard, and he begins to, in this paragraph here, state a few interesting facts. He says, scales help us measure the physical world, to compare quantities. And notice, measurement is about comparing. We mostly rely on quantitative scales, numerical measurements that tell us something about frequency and quantity. Inches, feet. He still doesn't get it right, because inches, feet, yards, miles, ounces, etc. are all units. They are not the result of measurement. A unit is just simply the realization of the fact that the outcome of comparing any magnitude by itself yields the unit. Okay? So then he says, what about qualitative scales? Well, actually, qualitative scales came before quantitative scales. So trust the British and everyone else to get it backwards. Quantitative measurement came after qualitative measurement. So he says these are the yardsticks that measure observable but not necessarily numerical properties. And he does make a few interesting facts here. He does state a few interesting facts. He says, qualitative scales allow us to label variables with little or no quantitative information. Generally, we can only say two things with qualitative measurement. We can say which one is bigger or smaller, or longer or shorter, if we can tell that they're not the same. Okay, so that it's really a dichotomy, which becomes a trichotomy if we can tell that they're not the same. These unusual units of measurement are often colloquial, guesstimations, as the crow flies. Now you'll notice that's something I used when I debunked the fallacy that there are axioms and postulates in mathematics in my first YouTube video, where I derived the concepts of position and line and extended line. So let's continue. He says, further on here, let's see here. Oh yeah, quantitative scales are much easier to evaluate since they are effectively comparisons to a known standard. Well, yes, that's kind of true. Well, actually, it is true, because we choose a unit by that time, and that's the only time we can have a quantitative measurement, once we choose a unit. Yes? Okay. And then he says, qualitative scales are more subjective. Actually, they're entirely subjective. He says, now this is the first error. Neither quantitative nor qualitative scales are, however, 100% accurate. That's false. Quantitative scales are 100% accurate. Okay? And I'll tell you, and he says they are each limited by the uncertainty baked into the definitions of units themselves. No, that is false. The unit has nothing to do with the derivation of the abstract number. Okay? So quantitative scales are 100% accurate if the measurement is complete. Okay? So, for example, if you're trying to measure the periphery of a circle with the unit chosen as the diameter of the same circle, that's not going to be accurate because you can't complete it. There is no way to measure the periphery of the circle, no matter what unit you choose. And that's easy to see. Take any circle of any diameter, and you'll still not be able to measure it, which means that regardless of any unit that you choose, you cannot measure the periphery of a circle, okay? Now, you may say, well, what if the periphery of the circle is 1? Well, then in that case, the diameter is not measurable. And you may say, well, surely we can choose pi as a measuring unit. No, because then the only thing you'll be able to measure is pi itself, okay? Same thing follows if you had to try a right-angled triangle. So what Adrian fails to understand is that quantitative measurement is abstract. It only becomes physical when we choose a physical unit, such as how many vibrations in a cesium atom amount to a second, okay? So only in that case does it become physical, and then, of course, it's not accurate anymore. All right, so it's a good article, a reasonably good article, but I'm afraid Bernhard still doesn't understand measurement, just like most of you don't understand measurement, okay? And I am the first and only human after Euclid to understand measurement. It's a big statement, but if you read my article, How We Got Numbers, and not read it, you'll have to study it, I'm afraid, you'll understand for the first time in your life what it means to be a number and how we got numbers, okay? So let's go back here. And then he continues to talk, and then Andrew Hansen, who is a member on LinkedIn, says there are things that we can measure and things that we can't. That's quite correct. Andrew, the measure of the magnitude is a number, okay? Did you get that? A number is that which describes the measure of a magnitude. Try to understand that. It's very easy to understand if you simply put aside all the nonsense that you've been taught in your entire school career and your university career. Your mathematics professors are absolute morons compared to me. They are, the difference between their intelligence and mine is like that between a human and an orangutan, okay, where they are the orangutans. So he says, but even what we can measure, we can only do to a degree. No, Mr. Hansen, it depends on what you're measuring. If you try to measure the periphery of a circle, you can only do that to a degree because you're quite right. The periphery of a circle can't be measured. But if you try to measure a given line using units, and that line happens to be a multiple of the units, then you have what's called a whole number, and it's complete measurement. You've actually measured it precisely with 100-degree accuracy. The same thing applies to a part of a unit, which is measurable because that unit chosen can be divided into sufficiently equal number of parts from which we can actually find the measure of a part of a unit, okay? Now, all that is explained in How We Got Numbers up here. So it says, yeah, Hansen works in soft metrology, studies measurements that relate to sensory scale, like color and light, etc. Blah, 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 not interesting stuff. And then finally, we get to the end of the article. I guess as some kind of conclusion, he says, measurement is the comparison of something unknown against something known. Nothing truer than that has been said, except by me, of course. That's what I've been saying all the time. Measurement is a comparison of something unknown against something known. Now, when you get to abstraction, it doesn't matter what unit you choose. You don't even have to know the unit, okay? Only in that case, you measure that unknown unit against itself. If it's the same unit, that same magnitude, then, and we choose it to be the magnitude of measurement, then it is the unit, and the measurement is complete, okay? So I'm afraid Hansen still doesn't understand that. So, and neither do you. Anyhow, Go to my LinkedIn article, which is over here, and study it carefully, because your knowledge of mathematics, and if you want to become a good mathematician, depends on you understanding numbers, because mathematics is about measurement, and you can only measure things with numbers. You can't measure it with ill-formed concepts like complex numbers or group theory or first-order logic or any of that crap. That's all crap. You have to understand what is a number. Okay, that's the first most important concept in mathematics. The second is the arithmetic mean. The second is the arithmetic mean. Okay, and I have much more to say, but I'm running out of time. So I hope you've enjoyed this little presentation, and this is the New Calculus channel. I'm John Gabriel. Till next time, goodbye.